Okay, can we start? The second talk of this morning's session is given by Olivier Collignon. Olivier is a researcher at University of Louvain, and also he is a researcher at CIMEC here in Rovereto. In fact, his first independent research position was here at CIMEC, so he is one of our superheroes here at CIMEC. But he was convinced to go back to his home country in Belgium, but he's continued to collaborate with CIMEC. The title of his presentation is Crossmodal Plasticity, and then there's a whole bunch of stuff after that. Olivier.
Okay, so it's a real pleasure for me to be back here. Like Alfonso said, I had my first PI position here, so it's a very special moment for me. Most of the work I will be presenting today actually have been acquired at CIMEC, so you will see a little bit what I did here. I've been attending this conference also for the last probably 4 or 5 years. I've been always impressed by the quality and the speakers lineup. So when Marius sent me this email to invite me, I thought like I should put that in the award section or the prize section of my CV probably, which was not that big, by the way. So okay, let's start. So what is the main goal of our lab? Is we try to understand how like specific brain region tune toward selective sensory input or specific cognitive function, right? So how does that develop? Obviously, when you try to address that kind of question, you cannot avoid entering this timeless debate about like how nature and nurture interact to shape the mind and the brain as we know it. It's a never-ending debate as is rooted in ancient philosophical terms with like this relatively strong opposition, at least as we typically, they teach us. The nativists, obviously, like Plato, Descartes, Kant, versus the empiricists that believe that the mind is a tabula rasa at birth, and like John Locke or Berkeley or Hume. And these people have debated philosophically, and then we enter this field, us as cognitive neuroscientists, to understand like how these two terms interact, because we all know that this dichotomy is quite trivial now. These two terms interact to shape what we know is the mind and brain. But this question, which I believe is still a very interesting question in cognitive neuroscience, is a very difficult question. And why it is a difficult question, and my argument is because of the redundancies that is there between people. We typically think about ourselves as very singular individuals that have a very strong personality, different way of interacting with the world. But if you think about it in cognitive neuroscience terms, it's actually not true, right? Across culture, people will see faces, hear voices, develop languages. They will interact with artifacts. They will extract emotion for communication. All these broad cognitive domains are actually extremely shared between people. And obviously, this is building on a very common genetic imprinting that we all share between us. So the interaction between these two terms is very difficult to address in the typical population. So what is the solution? One solution would be to go to the extreme, basically. To study people which have very, very different way of interacting with the world, a very different experience, and see how this change of experience impact on the development of the mind and the brain. And this is a little bit the path we have followed in the lab in the last 10 years. So to do that, we basically build on 2 model systems, which are early blindness and early deafness. And we try to look at it as cognitive neuroscientists in the brain and how this impact the typical region that have this strong imprinting to process one specific input, the occipital cortex for vision, the temporal cortex for audition. How does that change or not if you are born blind or deaf? just like open a bracket here. This is not an easy research to do. Actually, this, like I said, the research I will be presenting have been done here in Mattarello, which is basically in the mountains, if you think about it. So bringing all these blind people and these deaf people in the lab was a very challenging adventure. So I was very fortunate to work with a passionate team of researchers that managed to recruit as much early blind and early deaf people as we could and make them entering the scanner, which is another level of difficulties. And that creates like quite fun interaction, actually, in Trento. For example, this is a dinner with 8 blind subjects, so you can imagine the logistic of that. They come typically for 2-3 days. And this is a deaf group that came with camper and decided to do picnic in Mattarello, for example. So I think it's part also of the fun of doing this kind of research. This is typically done behind the scene. No one speaks about it, but this is really actually a huge part of the work. So to go back to the main goal of that, so what we try to do when we do this type of research, and I typically like to frame it like this, we try to causally test the sensory scaffolding hypothesis of the development, and then you can name it. Think about anything you would like to know if vision has an impact on, you can replace it there, right? You can study this function and say like, does vision impact on whatever? Color representation, color concept. I invite you to go to the poster of Roberto Bottini, actually, this afternoon. Then you can study that by using the blindness as a model system. And you can go on like this. One of the main overarching goals we followed is, like I said, like the organization of the occipital or the temporal cortex. One possibility is that nothing happened there. Right? Why? Because the wiring is so genetically imprinted that there is no room for change due to experience. Actually, if you read this quote from David Hubble in '88, a few years after he won the Nobel Prize, it's a very nativist quote, actually, right? He says, like, primary visual cortex and the few next stage wired entirely according to genetically printed instruction. That does not mean it cannot change. It still can change, but here require no experience, and whatever strategies, which I interpret as experience here, I used to bring that about could just serve as the fine-tuning, the dotting of the E's, the crossing of the T's. So basically, I think you can think about it, about like the fact that maybe nothing is happening there if you are born blind, which is obviously not the case, right? So this, at the same year, the first map of crossmodal plasticity. There was like previous work in animals. I think Josef Rauschecker, we speak this afternoon, did seminal work in animal models and then in humans on this. But in terms of neuroimaging in '88, this is really like the early age of neuroimaging. What you can already observe is that the activity in the back of the brain, the occipital cortex, is as elevated in a congenital blind as in a sighted with eyes open, and much more elevated than in a sighted eyes closed or in a late blind subject. First map maybe making us think that maybe something is going on there. What we do today, obviously, is we use different techniques. We don't rely on PET anymore. We use, for example, functional magnetic resonance imaging, and we do task-dependent activity. This previous research was actually resting state before it became fancy, actually. So this is a map that is very classically observed in our studies. You put blind subject in a scanner, you present them sounds, and what you have when you contrast what is more activated in blind versus sighted subject is this massive activity in the occipital cortex. So this clearly indicates that there is a reorganization process. The brain of the blind subject massively reacts to sounds and much more than what is observed in sighted individuals. Then, obviously, we try to go beyond that today and not just look at it and say, like, okay, wow, there is this reorganization. We try to understand the organization of this reorganization. So basically, functional specialization is their organization in this reorganized cortex, and all this organization relates to what we know is the organization of the occipital cortex of sighted individuals, for example, and the connectivity, right? We all know that this old-fashioned view of modular organization, quite independent from each other, does not hold true anymore. a function is a set of interaction with other systems, and we try to see how this recruitment of occipital cortex impact on a large-scale organization. So let's start with research, actually. So one thing we thought about studying is a very well-known system in the occipital cortex, which is typically dedicated to process second-order motion. Like, for example, if you contrast these coherently moving dots, even though they have a limited lifetime versus this flickering dot, you have typically that kind of activity, very reliable in single subjects. It's called typically HMT plus or V5, a region sensitive to motion in humans, but also in primates. So the question was, typically the classical view, actually when you see something moving, you typically don't only see it moving, you sometimes also hear it moving. Actually, most of the time, think about a car or on an object, right? And the classical view is that this kind of information, like flocking birds, will enter the system via two different sensory channels and represent themselves in the first step of the processing in the independent networks, one in the occipital cortex, one in the temporal cortex, for vision and audition respectively. And then they will get integrated later on, right? This is this classical hierarchical view where the integration occurs at later stage of information processing. But some people have thought that actually maybe interaction can occur earlier than that, right? That maybe this early stage of motion processing between auditory and visual motion processing can already create this kind of interaction. So this is one of the research we try to address, one of the questions we tried to address recently with Mohamed in the lab. So we did a relatively simple experiment. If you think about it, we presented like 4 directions of visual motion here using like a random dot kinematograms. And we try to reproduce that in audition. In audition, in the scanner, it's a little bit more tricky to reproduce 3D sounds. So the trick we use is we put people in front of a system of speakers like this. We insert microphones inside their ear, and we record from their own body the moving of information, okay? And then we replay that when they are in the scanner. This is very important, especially to create verticality, right? Because this is highly relying on spectral cues, and that are highly dependent on your pinea, body shape, size, and these things. So if I play the sounds to you, the sounds recorded in me, you probably will be unable to localize these sounds correctly. So this is the trick we use, and then we, like I say, we just reproduce this type of motion. So the first thing we do, we create a big localizer. We mix all these motion conditions, and we contrast that to static flickering dots or static bursting sounds, right? So this is what we call localizers. And this is what you get when you look at what is happening when you do an auditory motion localizer or visual motion localizer. Visual motion localizer, V1, as expected, and V5 are lighting up. And then this is the auditory motion localizer. The hotspot is in the planum temporale, as has been previously demonstrated. But here we see appearing this region, which is quite interesting, much more posterior region in the middle temporal cortex that barely people speaks about it. If we overlap that in a single map, actually, what we see is that there is this region highly sensitive to visual motion, which we will call V5, let's say. This region highly sensitive to auditory motion, let's call it PT. And then there is this region, which we still think if it's the good way to term it, but MT out, which seems to be actually more sensitive to auditory motion than visual motion, and this overlapping zone, all right? And when we extract beta activity there for motion which is dark or static, which is light gray, you see like this reverse pattern, right? High selectivity for visual motion, and then it progressively decreases, and then the reverse in audition, like when you go posterior to anterior. Little selectivity, but still, you can find trace of it, even in visual V5, right? And then it decreases progressively. So, and this is the reliability of these maps across subject is highly reliable, right? It's still, these maps are located quite reliably across subjects, so it's the percentage of overlap across our sample of 25. And then here it's, each dot is a single individual, right? So you clearly see the hotspot of PT, which is quite clustered, and then these two clusters, which let's say is V5 and MT out, even though they are close to each other, they are separate, right? You clearly see that there is an auditory cluster here and a visual cluster here, even though they are close to each other. Then we did a separate experiment. We said, like, okay, that is for motion processing, but can one of the landmark organization of visual motion processing is this directional selectivity, right? There is this columnar organization. There are some neurons that prefer some directions. Can we find trace of that using fMRI with auditory motion? So what we used is decoding, and we presented this visual and auditory motion separately this time, right? The left versus right and up and down and so forth. In a specific design, and this is the decoding results. So it's like the multi-class, the decoding and chance level is 25 because we have 4 directions, and we see that, let's say, there is like a distributed pattern of decoding ability, but I want to insist on these 2 regions. These 2 regions are quite interesting. Why are they interesting? Because they can decode direction of motion in audition and in vision, right? And one of these regions is actually what is typically defined as the purely visual V5 because it has been defined using independent visual localizer in each subject. Right? I hope you understand that we go inside each subject to find, so it's not a common region across subject. And we find here that there is decoding at least also in audition in this region. So we thought it's very interesting, so let's do cross-modal decoding to see if there is some kind of level of abstraction in the representation of motion direction in this region. So to do that, as you probably know, you train in one sensory modality, you train on vision and decode in audition, and reversely, and take the average of that in that case. And what we see is that the cross-modal decoding is significant only in right V5, but we still think it's quite interesting. So right V5, which is typically thought as a purely visual region in any textbook, not only as activity for auditory motion, not only can decode auditory motion, but you can do cross-modal decoding. So there is some kind of abstraction, some kind of common representation between these 2 senses, right? In this region. If you do a searchlight analysis, actually, this is really the only region that lights up. So it's very, very specific. It seems to only occur there. Because before it was arrow eye, now it's a searchlight, and it's very selective for right V5, this cross-modal decoding. Does that mean that this region is amodal or supramodal or does not care about the input? We believe it's not meaning that, right? Why do we believe that? It's just a simple multidimensional scaling here, right? And what you see is that there are very, very different clusters for audition and vision. So even though you can have information in both modalities, even though you can do cross-modal decoding, the geometries of the pattern embedded in this region are not similar. They are very distinct. What you see is that you pull across axis, so left goes with right, up goes with down, which is also remind very much the axis of motion organization that is embedded in V5. This is true for visual information. This is true for auditory information. But what is striking is this difference. Actually, this is not statistics. We did a series of experiments. I have no time to go through them, but we did a combination of modality decoding. Can you decode left in audition versus left in vision, for example? And you can do that very, very highly reliably. Okay? So you can very highly reliably. If you do representational similarity analysis and contrast like a modal model that does not care about modality or multimodal models that actually include multimodality in the functional tuning, the multimodal model explains much better the data than the amodal model. And actually, if you correlate the patterns there, you can have as much surprise as anti-correlation. So I will not go too much into the detail, but if you look at the reactivity to auditory and visual information, they can actually be out of sync, let's say. This is voxels and this is activity. We'll not, like I said, we're not too much into the detail. We can come back to that in the question if you want to, why we are able to cross-decode then. It's just regression to the mean, actually. But all this information are very informative to tell us that even though there is information in vision in audition, even though you can cross-decode, that does not mean this region is abstracted from sensory input, because you can find extremely reliable information that distinguish these 2 modalities. Okay. So that is one case about like multisensory. And so, like I introduced, what we try to do is like, okay, look at these systems when you remove one input. So you probably have understood the game now. We believe that there is this strong interaction between these systems. So when you remove one input, this system will be preferentially recruited by the connected region that do the same type of function, right? So this was the working hypothesis. We addressed this in a line of studies. The most recent one were done by Jeren in the lab. And one thing you can find back, so it's an independent sample here, right? And you find auditory motion here, visual motion here, auditory motion here, planum temporal. You find back again this empty posterior region, again, independent replication here, and this is the blind. You have this massive extension toward the posterior cortex to process auditory motion, right? So this is, visual motion and auditory motion in sighted and in blind. If you now represent these results on a singular map, in blue is what is common between sighted and blind for auditory motion selectivity, right? And in red is what is more active or more selective for motion, auditory motion in blind. And what you, here I forgot to put the outline, you have to imagine it, but there is the outline of visually defined V5 is here, and what you see is that there is this extension of the tuning for auditory motion in the blind compared to the sighted, right? You have this in the sighted and it seems to extend more posteriorly, but still specifically recruit a network that's still related to this function. And then again, you take this as arrow I, you do another study using the separate sounds, left, right, and this, and you try to decode. Exactly the same trick as the one we used before. And this is a very interesting pattern, we believe. What you see is that there is enhanced decoding in MT for the blind versus the sighted, and exactly a reverse pattern in the MPT. So it seems that it's especially true in the right side. We have this beautiful interaction here, meaning that the enhanced decoding in V5 in the blind goes end by end with a reduced decoding in planum temporale, right? So it seems that this reorganization process that seems to be functionally specific induced this large-scale imbalance between the two systems that are typically connected. And we thought like, okay, now let's do that with the other way, in the other way. If we remove audition now, and if it holds true, then we should probably see this kind of pattern, right? A specific invasion of the region that typically codes for auditory motion by visual motion, right? In congenitally deaf people. So we presented that. So this is a study that Stefania did lead all these studies in deaf people. And we presented that kind of stimuli, present like this moving pattern, like so here it's horizontal motion, you fix the cross and you have to tell me which one is moving faster. And then you have another condition of motion, like for example radial motion here, tell me which one is moving faster. And then you have another condition which will be a flickering condition. Why do we do that? Is to use a staircase method to be sure that, that basically they concentrate on motion and that the performance is equal between deaf and hearing people and across conditions. Because like this, we can play within the velocity between the two patterns and have exactly the same amount of performance between the conditions. And then we did also biological motion. I will not insist too much on that today. But so what do we see? So there's very fresh results here that Stefania provided basically this week. So when you look at visual motion, no surprise, right? V5 activates in hearing sighted people, and then look at the deaf, right? You have the same kind of network, V5 plus this region, right? Plus this region that activate, and then now if you contrast what is more activated for visual motion versus hearing, you have this single region on the right side which is overlapping with the planum temporale, and the outline here is what is selective in hearing people to auditory motion. So again, a very, very nice level of overlap. It seems that visual motion specifically recruit regions that typically code for auditory motion when they don't receive the feed-forward input. We did connectivity on that. We seed this reorganized region, okay? And we use PPI, so let's say, like task-dependent connectivity, what is more connected when you are doing motion versus non-motion, and you have enhanced connectivity in early deaf with bilateral V5. So this is the connectivity profile, which is enhanced with bilateral V5, so enhanced connectivity. And then when you do decoding there, so what you decode is the different type of motion planes that we introduce in the experiment. Again, the same pattern, very, very nicely mirroring what we observe in the blind, and hence decoding in the planum temporale of the deaf. Yeah, I forgot to say we always include a group of hearing controls that do sign language, to control for sign language. So we have always two control groups in these studies, typical hearing controls, and signers, typically, I mean, almost half of the sample at least is CODA, children of deaf adults, and then early deaf. So cannot really be explained by the practice of sign language. So this is a reorganization process that you find in early deaf. And then when you look at V5, the region that enhances connectivity with this region, it seems, if anything, to decrease its coding. The decoding accuracy is much higher because you are in V5 and you decode planes. It's much easier to decode planes than specific directions. But still, you have like this nice interaction here. So now let's go to another system. So this is another type of information where you typically use visual and auditory information. This is face-voice interaction. You typically do face-voice processing to infer like the identity of people, their emotion, their age, and obviously speech also that could, it's highly building on this audiovisual interaction. So now you know the game. So this is the classical model. Face and voice enter separate networks. They integrate at a later stage. Could be here, for example, PSTS. And people have proposed that maybe there is some interaction already earlier in the system. We have not worked that much on that, to be true, but there are quite nice evidence in the literature showing that, for example, here when you process voices of famous people, right, so voices of people you know the voice of, you activate a region that is overlapping with the right FFA. And this group in Germany actually showed that there is a direct track that links, so this is DTI, what matter connection, that links the right FFA with the right TVA, which is the temporal voice area region that typically preferentially responds to voice. So it seems that there is this white matter connection. So if this model holds true, you know the game, you remove one sense, it should be specifically invaded by the link functions. So we did an experiment where we contrasted, very simple, we started very simple, contrasted faces and voices, which are equated for low-level things like contrast, luminance, contrast sensitivity, frequency, sorry. And what you see is like when you contrast house versus faces, you have obvious PPA activation, more dorsal activation, the classical network, but we do not see much differences between the groups when we do that. Now when we do the reverse contrast, first versus house, you obviously see in both groups, sorry, I did not say that, this is hearing control and hearing signers. They did not show difference where we pooled them, and this is early deaf. So there is obviously FFA that activates as expected, and then you have this region now, right? And this region, so if you extract the activity of this region, you see that this is for face, this is for house, this is the two control group, and this is the early deaf. So it shows this selective activity in early deaf for face processing. And where is this region? If you do an independent voice localizer, right, it seems to overlap at least also again in the right side with the voice selective region, a region a little bit more anterior to the one we discussed about previously. If you look at voice selectivity, which is a turquoise here, and no, here it's face selectivity in the deaf, and the yellow stars are voice selectivity in the hearing controls. You see that they are really close to each other at the individual level. And in this experiment also, Stefania observed a correlation between the level of activity in this region and the performance in a face discrimination task. So we thought like, okay, let's do another experiment. Let's go one step further. We thought like this was the most amazing results we had since a while. So the other experiments say like, okay, this region, this organized region, can make the difference between a face and a house. Okay, but can this region actually do what FFA is typically doing, making difference between different faces? So what we did is an adaptation paradigm at different frequencies. I will not insist on that because it did not work out that well. We did not get very interesting or significant results there. So just like think about it as this is together. And this is blocks where there's different faces. They always change in size to try to control for low-level features. And blocks where these faces change in position and size, but it's always the same face that is presented. And what we do is take this region from the previous study, so it's independent. We localize this region in each subject and extract the activity for these things and look at release of adaptation. And what we see is that only in the deaf you have significant, so 0 is like no adaptation effect, so it's different minus same. And what you see is that only in the deaf you have this release of adaptation in this region. So so this is another way to represent it. So the only significance between the hearing control and hearing signer and the deaf in this region. So not only this region makes the difference between face and other categories, but it seems to also make difference between different faces, which is another level of computation. And then we say, okay, fantastic, let's continue on that. And we did an MEG study using the same stimuli as in the first experiment, the simple face versus house. And here we just like, so this is global field power, we just like look where there is a massive difference in the global activity of the brain between face and house. We localize that. Obviously it's MEGs, less precise, but it's in VOTC, so yeah, as expected, overlapping. There is no much difference between the two groups there. Then we look at the interact, so this is common between the two groups, and then we look at the interaction term. So what is more activated for in early deaf than in hearing control for face versus house, and we find back this region, right? So it's a very independent replication. It's the same stimuli, same subject, but a different imaging modality. So you say, yeah, it's normal, but we were still quite happy to see that. And now we take this region that were localized in fMRI, and we put a virtual sensor in this region, and we extract the temporal dynamic of this region using the MEG data. And what we see here, it's in hearing controls, in TVA. So this is for face and house, right? Face is blue, house is red. You don't see much activity in hearing controls. In FFA, obviously, you have this difference. When you localize FFA, you have more activity for face versus house, peaking at this typical, let's say, time point. And when you look in the deaf, in FFA, you have also this difference around the same timing. It seems a little bit lower, but it's not significant. And then you have this enhanced activity in this region. But what was quite interesting for us is to see that it appears only a few milliseconds after the selectivity that you observe in FFA. So it does not tell us exactly how the information goes there, but it tells us that the information goes there very quickly. Right? So I don't know if it's still going through FFA and then to TVA. Actually, we did some DCM, and it seems that actually there might be also some kind of parallel processing in these regions. And so you remember, I showed you this study that was showing white matter connection between FFA and TVA. So we acquired DTI in this population, and we try to first reproduce. Can we find back this track? There was only one paper on that, and we can reproduce it. So we can find this track. Here it's this one. We try to find two tracks, and we were successful in finding a track which is more between V3 and TVA, and this FFA TVA track, so the same as in the blank paper. So we found that actually this is a single subject where you do the tractography embedded in his, let's say, white matter connectome. And when you look at least at the macrostructural probability of finding this track in deaf and hearing controls, it's a similar probability. So you do not have a difference between deaf and hearing people in the probability of finding these tracks. If you look at more microstructural reorganization, like so radial diffusivity or functional anisotropy, you have differences between the two groups. I'm not sure, I'm not a DTI expert, what exactly does that mean? Maybe crossing fibers, these things. But anyway, at the macroscopic level, the tracks are there. And what we believe is that this is the presence of these tracks that explain how this cross-modal recruitment is that functionally specific. So now let's do the reverse, the blind, and for the first time it does not work. So, I mean, so far so good. It was a hit in everything. And then we thought like, okay, if this theory really works, FFA will now in blind react to voice specifically. And that did not work. So we don't know why. We are still working on that. There are two possibilities. We have nice selectivity for object sounds, actually, in LO. So that works quite well. But for voice in FFA, we don't have it. Sorry? 3 minutes? Wow. Okay, so I'll take 5 more minutes. How much do I have? 5, thanks. A little bit late, I think. Okay. So let's go quickly. So there's two possibilities there. One is that there is region dependence in the possibility to observe this cross-modal plasticity. So FFA might be a specific case, and so is imprinted differently and has not the same possibility of reorganization. I think actually some guys like Marius, Alfonso bring some kind of very nice data suggesting some kind of difference between animacy, inanimacy, and the animate region actually have very different functions, so maybe might be difference. That may be one way of thinking about it. The other way is that we did it wrong, which is a possibility because we did not ask people to focus on identity. We asked them to process voices amongst other objects, but did not ask identity processing, and that might be also the key. So the intermediate conclusion is that we see cross-modal plasticity, so experience plays a role, but this is functionally organized. So then there is an imprinting, there is like a constraint that is applied on this reorganization. I will skip that. I'm sorry about that. I thought I would do better on time. It was quite fun, sorry. Maybe in the question we'll go back to that. So this was about language processing in the occipital cortex. Because one main challenge for this theory that I'm trying to suggest here, which is like cross-modal plasticity, when it expresses following functional rules, functional guidance. But we know also that eye-level cognition also map in the occipital cortex. What I mean by eye-level cognition, like for example, language processing. So you have all heard about that. Marina Bednik came here, I think, a couple of years ago presenting data about that. It's a little bit more challenging to think about how language will remap onto existing functional principles of the occipital cortex. My previous slides was about like a proposition for that, so maybe we can go back to that in the question. Actually, we also observed that, but we think it's not abstraction. It still relates to the input, and maybe this face-voice interaction can explain why language may also root in the occipital cortex. But we did with Virginie, that is here, doing a Mercury in the lab, another experiment using arithmetic processing. So arithmetic is another example in the last years that has been used to say that the fact that arithmetic processing numbers, symbolic numbers, also recruit the occipital cortex, and then these results suggest that the human cortex is highly functionally flexible in life, and you can read that actually it takes another function, a function that is not rooted there. We have a different view on that, obviously, based on the background studies I've showed you, and we thought like actually arithmetic is a very interesting example to build on. Why? Because you can do different kind of arithmetic operations, and this will recruit separate networks, right? So if it was just like very high level, which I don't know what it means, don't ask me, but high level recruitment of occipital cortex that is more like the tip of the iceberg or the final stage of the hierarchy, we should probably not see much differences between different kind of operation. But what we did is like we contrasted subtraction. So subtraction is like this kind in a block design. What you do, you present to the subject, you say like, you have 7 before the block, so 7 is the target. Then you present 2 operands, so 13 and 6, and they have to say like 13 minus 6, and is the 7 that I have in mind the correct answer or not? And they have to say, yes, indeed, this is the correct answer. And sometimes the operation is different. And we do exactly the same trick with multiplication. We tell them, remind 21, okay? And then they enter to the block, and we present 3, 6. They know they have to multiply these two things, and then they have to say yes or no. Is it 21 the correct answer? And in this case, no, it is not, right? Because it's 8. So we do these things. So they're very similar, right? You play with symbolic numbers, you do arithmetic calculation, but we know from previous studies that they typically recruit different networks in the blind, and in the brain. And typically subtraction tasks, like addition tasks, involve more spatial processing of spatial manipulation in the mind. And multiplication is more a memory style or language type like of operation. This has been proposed. We are not the first to propose that. It has been demonstrated, but we really nicely replicate that. So if you contrast multiplication over subtraction, and in yellow here is the conjunction between blind and sighted individual. So for multiplication, you have mostly a network that is located in the temporal cortex, maybe orienting us toward the thinking that, okay, maybe they use maybe linguistic or, I don't know, memory. I'm not exactly sure of what is the computation, but this is at least what is very interesting. It is a very separate network than the reversed contrast. When you do subtraction versus multiplication, you have this beautiful dorsal network, right, including IPS, region very close to the frontal eye field, and frontal gyrus here, this region. And then now look at when you contrast blind versus sighted for subtraction versus multiplication, there's very nice right-sided dorsal recruitment. And this should now probably induce some thinking in you. These are regions that overlap with visual spatial processing in the sighted subject, right? And what we say is that these networks activate more for subtraction because actually there is more like some kind of spatial processing in that type of cognitive operation. Actually, if you overlap this map in subtraction versus multiplication from maps that we acquired previously, where we contrast auditory localization versus auditory pitch, it's very, very different, right? And auditory localization versus auditory pitch activate also this right dorsal network with huge overlap between subtraction and multiplication. So what we believe is the common cognitive operation or cognitive term in these things is space, right? There is some kind of spatial processing that is rooted in this region, so this region reorganized specifically for some even high-level cognitive function, still following these guiding rules. We do some connectivity, and it also shows connectivity with the dorsal network. It's my final slide. So what I hope I've at least partially convinced you about is that cross-modal plasticity is not a stochastic phenomenon. It's not at all random. Okay? It's following rules. It's there. It's massive, but it follows guiding principles that we believe are intrinsically there in the brain of sighted individuals. So it relates to the native computation. And what is the link? It's potentially the connectome of the subject. Maybe how each region connect with some friends to do the same kind of play, same kind of cognitive operation. It imposes a large-scale redistribution. This recruitment of the occipital cortex does not leave the temporal cortex, for example, in the blind, and reversely unaffected. It seems to induce this balance game between the two. So enhanced tuning in the deprived region seems to apparently, in our data, reduce the tuning in the native cortex. And what we like to insist on is that these data does not mean that it's this reorganized region, let's take V5 in the occipital cortex. It's not a duplicate of PT, right? It's not smart to think about it that way, but it's neither a replicate of V5, right? It follows guiding principles, but these guiding principles are there to constrain plasticity, but it does not mean that the computation should necessarily be the same with the one done in audition or the one done in the sighted in vision. It has a common grounding, but it's not necessarily the same computation. So I'll finish by acknowledging all the fantastic team that worked on this data. It's really, believe me, a large amount of work to put all these people in the scanner. So this requires large resources. We are fortunate enough to have an ERC, and now we have a print project from the Italian ministry that Roberto Bottini is leading in Italy at the moment, continuing that kind of research, going more to the conceptual representation. And obviously, thank you very much for your attention.
Thank you for the nice talk. You started your talk with David Hubel, and I knew David quite well, so I feel obligated to defend him a little bit. You kind of quoted him as if he was a pure nativist, which he was not, of course. He and Thorsten Wiesel made one of the biggest discovery on plasticity of the brain in terms of monocular deprivation effects and so on, and that's well known. And so I think David would have liked your results very much, because I think what you show, although in your last sentence you were kind of sort of a little relative about it, but I think what you showed really, and what most of the findings in the field of crossmodal plasticity show, is that the essential computational functions that a cortical area performs remain largely the same, plus minus some, modification. But your MT results are beautiful in that sense. And what really happens in plasticity is you get a reassignment of the sensory modality. So that same module that does motion computation in the visual system then kind of does a similar computation in the auditory modality, or maybe even in touch, in the tactile modality, as some of our unpublished results show. So I think this is the essence of crossmodal plasticity, and Hubel and Wiesel would certainly, underwrite that. The only problem I think that they would have is with some people now claiming, and this is sort of an old claim that is coming back suddenly, that visual cortex can be as pluripotent as you wish, in terms of taking on language functions. So you seemed kind of skeptical about that too, and I'd like to hear more from you what you think about this possibility or not possibility.
Yeah, thank you very much. Actually, I knew it was a risky business to put that slide, but I thought it was fitting nicely with creating a little bit this tension. But I was not fortunate enough to know a bell and whistle, but yeah, I mean, it was amazing discoveries, obviously, but still intramodal reorganization, right? So mostly building on ocular dominance column, reorganizing themselves and these things. So here, going toward like the invasion of another modality, as you yourself showed very well, was, I think, another step toward this possibility of the cortex to reorganize and to know that the fact that auditory function will now mesh really literally with the functional tuning of these neurons. So yeah, I would have loved to debate with them, because they were still speaking a lot about visual neurons, these people, and what we see is that these neurons potentially fire to sounds, right? And what does that make these neurons for then? And these kind of very interesting debates I would have loved to have. So going to your second point about so the challenge now is to try to reconcile this view, okay, the functionally specific view, with the idea that language, let's say, to take I spoke about arithmetic, I hope it was convincing, but for language, it's true that it's potentially even more challenging, and then the idea is that these regions are pluripotent, a little bit like the Meringue-Cassur experiment, right? When you reroute the visual tracks into the auditory cortex, then you start to have like some kind of organization like the visual system. So then the neurons just tune towards the input they receive. First, my take on that is that they receive some specific input. So if language function across blind individuals map into specific location of the occipital cortex, which is the case, it's not in one subject here and another subject there and these things. So it means that there is a principle. It means that there is a route, a functional route that the input is taking. And then I think the only smart way to think about it is to think that this route that they are taking is a route that has a function. So otherwise, why would this route be there, right? So what could be the function of this route? And my take on that, it was a little bit what I tried to make an interest. So if you look at this, you will get it probably, right? Okay, so we lip read actually, right? We constantly extract from visual information, auditory information. There are very nice work that show that there is phase resetting in the auditory cortex when the lip starts moving, because the lip starts moving before the sound is produced for obvious physical reason. And this creates a resetting of the phase of the activity in the auditory cortex in monkeys and apparently also in humans, right? So there is a route there. Falchier, from the group of Kennedy, for example, show monosynaptic connection between the primary visual cortex and some region in the auditory cortex. So, yeah.
Yeah, but this is not the claim in those recent studies where I think the claim there is that top-down projections coming from the frontal cortex can begin to drive neurons in the visual cortex, and that would be the underlying mechanism for language processing.
Yeah, so this is definitely
cortex.
A possibility. This is definitely a possibility. So I think this gives us like exciting moment for the future to look at that. We did this speech tracking study, so you probably are familiar with speech tracking, right? You extract the envelope of speech, the rhythm of speech, okay? You have this change of energy across time that typically track the syllabic transition rate that is in the signal, and you correlate that with brain activity, right? So this is typically brain region that will entrain somehow to the rhythm of speech. And you contrast when the speech is intelligible versus non-intelligible. And what you find is that the occipital cortex of the blind track the rhythm of speech and is sensitive to intelligibility. So it cannot be, and you don't find that in IPG, for example. IPG do not track the rhythm of speech and is not sensitive to its intelligibility because it's doing something else. So the region here that in a control subject that track the rhythm of speech, so basically where neurons entrain to this syllabic transition rate and are sensitive to the intelligibility of this speech, are region in STS, sorry. And this is this region that reorganize in the blind. So it does not tell us exactly what computation is there. I'm not claiming that. What it's telling us is that's maybe less abstracted or eye level or IPG style, which I don't know exactly what it does, type of computation. We still believe that maybe there is a sensory grounding, a link to the signal that is there, and this link to the signal, actually we did connectivity between this region, and we show enhanced connectivity in the blind. So what we believe is still, in our viewpoint, that this direct connection between the occipital and temporal system explain this cross-modal recruitment instead of the more feedback route. But this is fantastic that there are people that believe otherwise. Like this, we can continue to work on that.
Thank you. Very nice talk. So at the very beginning, you put up these slides, these photos of your congenitally blind that came with a camper, which made me wonder who drove that camper. But that's not my question.
It was the deaf.
Oh, that was it. Okay, I mixed it up. So my real question was, how fast do you think these changes happen? I'm reminded of the early studies of Lofty Marabet, for example. So if you were to blindfold your participants, how long would it take for you to see those changes?
Yeah, it's a very interesting question. So as you probably know the work of Pasquale Leone and Lotfi Merabet, for example. They've claimed that 5 days of blindfolding is enough. So if you blindfold people for 5 days, you start to see this increase of activity in the occipital cortex. And what was even more fascinating and puzzling, also if you think about it, is that then if you do TMS on this region, it impairs tactile processing, which is very fascinating. So if we follow these results, okay, then it's very quick. And then maybe it's not that strange if you think about it. If you think that actually the native connectivity between functional systems is what explains this recruitment, maybe that potentially this unmasking of connection and these things can be relatively fast. I have personally more reserve because I've worked also with late blind people, which is another very interesting model to work with. And if this is true, if just like 5 days of blindfolding makes the same results as early blind, so then the late blind should have even more the same results as the early blind. And this is not what we observe typically. Typically, the plasticity is much lower than what we observe in congenital blind, so the recruitment is less, and it's less functionally organized. Marina Bedny showed that for language. They don't have language-specific activation, and we showed that for spatial processing. They don't seem to have this very nice right-sided dorsal activity. We have not tried yet with motion, with the late blind. Motion, I think, would be very interesting based on the results we have seen. We planned to do that, but we had some other constraints. But I think it's still an open question. Also, when you think about it in terms of sight restoration, I know I open a new door here, but what is the outcome of sight restoration in a congenitally blind versus a late blind subject, for example? Typically, the outcome is very bad in a congenitally blind and very good in a late blind, right? So recovering sight at 40, when you have never had vision, actually makes you a very poor-sighted person. If it's late blind, you lose your sight for 3 years due to corneal disease or dense bilateral cataract that is not detected or cured quickly. When you have this operation done, they recover sight quite easily. So it's still, this reorganization in the congenitally blind seems to be rooted really in the occipital cortex. And what do I mean by rooted is I mean that it's functionally specific. So another way of responding to that is TMS. You do TMS in a congenitally blind subject, occipital cortex conjunctival subject, you disrupt sound processing. It's not really the case in the sighted, it's not really the case in the late blind, or at least it's much less there also. So it's yeah.
Hi, really nice talk.
Thank you.
I wanted to ask you about the functional consequences of the plasticity, independent of whether the computations are of the similar sort. One would expect there might be functional consequences to devoting more cortex to something. So if the congenitally blind are doing auditory processing with the ordinary auditory areas, but also with what would be visual cortex elsewhere, what are the consequences of that? I mean, how much, I know not necessarily in your work, but can you just what sorts of evidence there is about functional consequences?
Yeah. I mean, it's a very obvious and good questions. In short, we don't really know, okay? There are some works, so I mentioned the TMS work, right? So it seems to not be epiphenomenal. So the activity there seems to do some kind of processing, because if you interfere with this activity, you interfere with the behavior. So it seems to be functional. Then what does that involve in terms of, okay, or do they process sounds, or do they recognize objects and these things? Are they better because they have more cortex and these things? Some studies have suggested some links, like for example correlation, which is obviously not causation, but between the amount of activity. We have that in one of our studies, the deaf study. You may remember the more the deaf recruits this TVA region, apparently the better they are in the Benton task to face discrimination across orientation of the face. But I would be very careful in saying that. I know that it's a very, typically people will jump on that and say like, yeah, they are better, we know that the blind are better, we know that the deaf. Actually, if you look at the amount of plasticity, so it's massive. They should be like superhuman and able to whatever do things, and it's not the case. There's limits. Yeah. Yeah, but this I argue it's relatively subtle differences. I think there are beautiful differences. We show that, for example, for auditory localization. Yeah, it's true. Yeah, so it links to the TMS because this is the schooling technique. Yeah, but then you have to prove me, because these deaf or blind animals or humans, these models, like what you have to show me is that because obviously blind people, they also train more in sound discrimination. Like, for example, you have beautiful works on echolocation, right? You have like blind echolocators. This is quite a fantastic ability, but that does not mean that sighted cannot be echolocators if they are trained to do that. And they will not start to have this massive reorganization because they don't have this leftover cortex and these things. So linking the reorganization to the enhanced behavior is a tricky thing, I believe. It's a tricky thing, and also just like in principle, linking any brain region with a behavior is a tricky thing. Taking the activity in one brain region, extracting this activity, correlating with a behavior that necessarily multifactorial, let's say, is very, very difficult, because a behavior is obviously a set of interaction in the brain, and you cannot isolate one behavior with one region. So linking these two, probably it's smarter to try to correlate the connectivity fingerprints, actually, the reorganization in that, and behavior, then maybe we will be more successful.
Yeah, I agree, it's complex. I think it's worth pointing out, though, that from the earliest study of plasticity, there's been less emphasis on the functional consequences than on the neural consequences than perhaps would be useful. And I think animal models are a really good way to go with that.
A similar question to Mike. You know, I'm fully convinced by your beautiful work and others of reuse or alternative use of other systems in arithmetic or speech, as you're showing here. It strikes me one possibility is that the function to which other regions were devoted, you know, related to speech or arithmetic, has been moved to a new part of cortex, and maybe that's more true in you know, congenitally blind or early plasticity than in later blind. It seems equally possible, the other extreme, that it's the exact same computation, which is inherently governed by the cell types and the circuitry and inputs and outputs and so on. And so the nature of the function has changed. And so I think there's a temptation in looking at the sort of use of new systems to assume that it's the same computation, it's just moving somewhere else. But that strikes me as a much grander claim in terms of plasticity than the nature of the behavior has changed. So it's sort of rehashing what Mike was saying, but I do wonder to what extent you can make predictions about how the behavior should change based on the known computations of a region, and test that psychophysically or behaviorally. Yeah, that is a very good point. I mean, we try to think about that. It's probably, you understand, it's a very difficult, like I said, like linking really the activity of one region with one type of behavior. It's a tricky thing. I still believe that your other radical hypothesis is impossible, right? That the function will completely move to this region. Why? It's just because of the data. I mean, first, to me, it does not make sense. But second, the classical regions still activate, right? They are still there. They don't disappear. They still have, the blind is still an auditory cortex that processes sounds in an organized way, like the way we know it. And there is not much reorganization there. There are some specific intramodal plasticity, but it's much less salient than what we observe in the occipital cortex. So nothing paralleling what we observe in the occipital cortex. So it's not moving.
So
is it fair to summarize your position then as coming over to the position I advocated with you over years and you were disagreeing with, in other words, that you're a nativist?
That I am a nativist.
I'm a nativist. I'm saying so are you. That is what you've argued, if I understood correctly, is that the functions that are taken over are only taken over if in fact the structure is already in place for those computations.
Yeah.
Okay. In other words, your argument actually is not that the plasticity leads to new computations. What it leads to is the same computations with in areas that were already organized for those functions. Yeah. And in fact, if you look at the language data, for example, well, certainly the data that Yan Xiaobi, Mario Spillin, and Wang and we have produced over the years, showing that the pattern remains the same in the blind, congenitally blind. And if you look at the language data in the way in which you interpret it is not that, in fact, if you look in occipital cortex, you find a move computation or a morphological computation. What you seem to be saying is that you have an input that's already pre-existent, and then this input aids or converges back on language areas, so that the occipital cortex is not computing linguistic representations. Or at least, if it is, no one has shown it. So in fact, I think the bottom line is that you're a nativist.
I would actually... Just for the principle, I will disagree with you. But, I mean, I don't think, I mean, obviously this nativist empiricist is trivial, like I said, right? So, yeah, I am an interaction, right? So the point is that what I mean is that there are guiding principles that are intrinsic, and that could be the connectome. That could be an intrinsic wiring between regions that share the same function, right? For example, V5 will link to... Then, wait, you have to wait. So then does that mean that, for example, there is innate knowledge or innate computation in this region? No, right? So this needs... So I was knowing it will come. So what I mean, okay, let's try to simplify. You have feed-forward input, you have feedback input, you have this region that is typically linking the two, right? Let's say VOTC, right? You remove the feed-forward input. What remains? The feedback input. The feedback input is organized, will drive what will happen in this region when it's not receiving its feed-forward input, right? Does that mean that the computation that will end there is random? No. It will be linked to the node that is in this system. Does that mean that the computation that is there is the same as the one in vision? No. Because the one in vision is also driven by feed-forward input that is not there in the case of blind people.
I think that when you talk about nativism, there are two ways in which we can interpret it. One is that you actually have ideas in your head, but that's a very difficult concept. Certainly, we seem to have just the kinds of ideas our brain can compute. I don't think you can dispute that. And so there's a sense in which nativism may actually be a much more reasonable theory than some people have tried to make it sound. So, for example, all of the work on developmental, early development of people like Lispelke and so on, showing that there are some core principles, and those are there from the get-go, and they are the same across cultures, across all kinds of experiences. So that, in fact, in that sense, they are sort of inborn kinds of things. Now, it's not that the idea of refrigerator is inborn, okay? But the idea that you can have an object and then can be fleshed out by experience is something that is, I think, trivially agreed on by everyone. So to go back to the question, there is no evidence that I'm familiar with that shows that areas take on new computational functions, okay? New representational types, okay? That is what you have to show to argue that experience has an effect. Okay? All anyone has shown so far is that, in fact, when you get reorganization, it seems to follow the exact pattern in the normal system. Okay? It doesn't deviate from that. So I think the bottom line is, even though we don't like the word nativism, that in fact the neurobiology seems to suggest that we should be nativists.
Yeah, at this level of organization, I agree with you. Yeah. So then I think maybe, and I don't know if it's interesting, really, seriously, but if we now try to go in the question of what is the computation, because we say computation, but what is computation? I don't know what is computation. Maybe you can tell me what is a computation implemented in a brain region. I sincerely don't know. But if we, so the only formal way to test that in a Popperian sense of the term, so how can I refute my theory and these things, right? So is to have a definition of what should be observable, and so the idea is like, it's exactly the same computation, you said that, right? You say it's exactly the same kind of operation, or I don't know exactly the term.
The same representation.
The same representation. So then we need to say if it's exactly the same in blind and in sighted, or in vision and in audition, you should not find any trace of differences between these two things. And this is obvious that we find trace of it. So at that level of thinking, it's not the same thing. What does that mean? I don't know exactly what is the type of representation, but the overarching goal of the region is maintained. I agree with that.
Let me push on this just a little bit. I don't know what the brain is capable of and how much change and so forth, but let me go to your example of arithmetic. Okay, so in order to make this seem consistent with your argument, you suggested that the difference between subtraction and multiplication is that subtraction is spatial and multiplication is not, and therefore subtraction could fit more into a visual area because it's spatial. I guess I'm not clear on what the basis for that assumption is. Right, so multiplication, as I would think of multiplication, at least this simple sort of subtraction, multiplication you're probably more likely to do by having memorized that 3 times 6 is 18, whereas subtraction, well, if you did what you're supposed to do in school, you would just have memorized that 13 minus 7 is 6, but maybe you didn't do that, and so you're doing something more like some other manipulation where you're to addition or something like that. I'm not sure that I see one of them being more spatial than the other. And so I'm wondering whether the assumption of subtraction being spatial it's convenient to fit within the hypothesis, but is it independently motivated?
Yeah. Okay, so I will start with the wrong argument. Okay, the wrong argument is it activates this dorsal network, which we know implement that type of computation, which is some sense of reverse inference. So it's not good to do that. You don't infer a function based on previous studies or these things. Then the other things is that there are people, not me, I'm not working on that, but that show, for example, this operational momentum effect. I don't know if you're familiar with that. If you, for example, do multiplication, so for example, you have in mind plus, and I present you 3 and 7, it seems to orient your attention toward the right. If you now flash a target in the right side, you go faster after this kind of operation, and you do have the reverse effect if it's the same numbers, but now you have in mind subtraction. So now it's 7, 3, right? You have to do subtraction, and you flash a target, you go faster if it's on the left. So it seems that there is this displacement of attention that is following some kind of way we think about it in our mind, right? So that is indirect evidence that we use some kind of spatial layout to do this number. And then there is the classical snark effect and all these things and these things. So that does not necessarily relate to subtraction by itself, but I'm building mostly on previous works here. I'm not working myself on that.
Thank you very much for this discussion. Thank you. Time to come back. Please come back sharply at 2 o'clock.